Hello and welcome to the Embedded C Programming Design Patterns course. This course is available here on YouTube, and also if you don't want to wait until the next module comes out, you can get this course as a book, as book plus videos, Udemy course, and also all of the book and video content, as well as live sessions with me on Wednesdays, which is available at swedishembedded.com. So the book is available on Kindle. You can download it from Amazon. The Udemy course contains the book materials as resources, as PDFs here. And on the website, we have the course available as a standalone course directly on the website. You just click join here, enter your details, register as a student, and then you will have access to all the course materials and also the weekly Q&A, which is in 5 days, 8 hours at the time when I'm recording this. All right, so let's get on with the next module of this course. Hello and welcome to another module of the Swedish Embedded Design Patterns training. My name is Martin Schroeder, and if you have any questions regarding this training, you can join our Discord channel. You'll find the link at swedishembedded.com, or you can email me directly at martin.schroeder@swedishembedded.com. In this module, we're going to look at the Spinlock pattern, and this is the first pattern where we control concurrency from the hardware layer onto the software layer. So this pattern allows us to control data access between our code and code that is executed by the processor or triggered by the processor, for example, like the interrupt handlers. And also, it allows us to control data access between multiple CPUs. So it's the bottommost pattern that connects to the hardware. And then on top of this pattern, we can build other concurrency patterns, such as semaphores, mutexes, conditional variables, and basically anything else that that depends on that needs to implement any kind of concurrency. So this is a very fundamental pattern, and understanding this pattern will help you then understand how other concurrency primitives work, because they all use the Spinlock at the bottom. The defining characteristics of the Spinlock is that it consists of an atomic variable. We use the atomic variable to synchronize data access between multiple CPUs. It has a tight loop when it is locked on multiprocessor systems. So it can, by doing that, it can wait until another CPU releases this variable. And it also does interrupt masking. So it disables interrupts, allowing us to control data access between our code, regardless of whether it's a code that runs in a lower priority interrupt handler or if it's our application code. And when we disable interrupts, we are able then to be sure that whatever we are doing between locking the Spinlock and unlocking the Spinlock is going to be a critical section with only one thread on one CPU having access to that data. We use the Spinlock pattern to synchronize access between code and interrupts, and to synchronize access between multiple cores. This is different from, for example, mutex, which is only acting on threads. Mutex is a thread-aware primitive, so it allows us to synchronize access between multiple threads, but the mutex doesn't give us synchronization between our code and interrupts. So a Spinlock is something you would find in the operating system code, which actually interacts with the same data structures as our interrupt handlers. The benefits of making this into a standardized pattern is that we get a generalized approach for synchronization between code and hardware. We can make sure that our code works on a single processor system as well as on a multiple processor system. And it's also extremely lightweight. So it's a mechanism that doesn't have any thread queues. It isn't even thread aware. So it is very lightweight, and it's designed for very quick locking. So you just lock for very short periods of time where you need to access shared data structures, and then you quickly unlock the Spinlock. And it's also usable in interrupt handlers, although you usually wouldn't have interrupt handlers that share data. But if you do have that, then by disabling interrupts, inside an interrupt handler, you can actually achieve synchronization between higher priority interrupts because they wouldn't be able to preempt your current interrupt handler. So it's a very low level primitive, and it's important to understand this because when you hold a Spinlock, no other event can happen on the current CPU. You're holding back essentially all of the hardware interrupts. So if you hold it for too long, you can run into a situation where you delay the handling of an interrupt too much. So you have to be very precise with what you're locking and never hold this lock for too long. The drawbacks of Spinlocks and why we don't use Spinlocks in higher level code is because Spinlocks have no concept of threads. That's the main drawback. So you cannot queue on, you cannot have multiple threads queuing for a Spinlock. You can only have multiple CPUs queuing for a Spinlock if you have a multiprocessor system. And the second drawback is that it actually disables interrupts. So if we look at, for example, a mutex, it doesn't disable interrupts. It only disables interrupts very momentarily when it acquires the mutex, but when the mutex is held, the interrupts are still enabled. So all the events can still be processed, and the mutex is essentially just preventing multiple threads from accessing shared data structures. Whereas Spinlock actually disables interrupts, so no event can be processed during the time when you're holding a Spinlock. All right, let's move into the implementation section. And in this section, I'm actually going to show you C code that implements a Spinlock. But before we do that, let's look at some of the key concepts here that we use when we implement a Spinlock. So number one is we have a global interrupt mask. And on ARM architecture, this is called a prime mask. And this allows us to basically disable maskable interrupts. And some interrupts are obviously non-maskable, such as, for example, the reset interrupt, which gets executed when the system starts. But most interrupts would be maskable. And we can implement other concepts where we can have some of the interrupts that are not maskable. But the thing is that if we use those interrupts, then we shouldn't, or we actually cannot share any data safely with those interrupts unless we use non-locking algorithms when interacting with the same data structures. So for the most part, when we use Spinlock, we would be dealing with maskable interrupts, and we would be disabling those interrupts when we acquire the lock, and then we'll be restoring the interrupt state when we release the lock. Then we have the interrupt priorities. I hope that you have some basic understanding of interrupt priorities and how interrupts can actually interrupt each other depending on the priority that they have. And that you understand that interrupts are triggered by the CPU, and it's basically the hardware level of preemption, where we can be interrupted at any time and the CPU will jump to another function, execute the interrupt handler, and then return to where it was before. And the Spinlocks, we're going to use the Spinlocks basically to synchronize the data access between our normal code and any code that runs as part of an interrupt handler. And we also have the base priority, and this is also a special register that controls which interrupts get disabled when we call the interrupt disable instruction. So this gives us a little bit more control of our setup of priorities and interrupts, and we can use this to create more responsive systems. But we're not going to go into details about the base priority and things like that. You can look into the ARM documentation to see how this works on ARM, and on other architectures it's going to be a different approach. But the basic idea is that we have some interrupts we can disable, other interrupts that are low latency interrupts, which where we need to follow special considerations. And then we have our non-maskable interrupts, which basically always execute, and usually a non-maskable interrupt means that there was some fatal error that occurred in your application. So we don't care about those. So the main problem we're trying to solve here is sharing data with an interrupt handler. So we're interfacing to the lowest level of hardware. We have some data here. Let's say we have a data structure. It has some variable inside it. And we then share this data structure with an interrupt handler that does some operation on this data structure and writes a value. And then we have some user code that also reads this variable, adds something to it, and then writes back the result. And if we were to execute this code, and let's say we can get this interrupt routine to execute at any given time. This is basically connected to a hardware interrupt, and so at any given time the hardware can interrupt whatever we are doing and execute this routine. So what would happen here? Well, when we are executing this operation, we might get interrupted in the middle of this operation, and then 5 would be added to a value and written back. But then let's say we have already read the value and we're adding 8 to it and then writing back the result, we would get the wrong result, because this operation will be, the result of this operation will essentially be ignored in such a scenario, and the variable will get its old value plus 8 instead of its old value plus 5 and then plus 8. So this is the situation we're trying to solve. And Spinlock is essentially the pattern we use to solve this kind of problem. We can get a better understanding of this problem by looking at the disassembly code of these operations. So for example, our operation which adds 5 contains multiple instructions here that basically read the value, add 5 to it, write value back. And the same thing for the user code. We have multiple instructions here that execute. Now, for the user code, at any place here, we can get interrupted by the interrupt handler, and then the interrupt handler can do its thing, finish off, and then we'll go back to where we were before. And so the result would be wrong, obviously. So we need to protect this section in particular from being interrupted by an interrupt handler. We don't need to protect the interrupt handler because basically as long as the interrupt handler doesn't get interrupted by another interrupt handler which also modifies the same data, we'll be fine. But for the user code, we need to protect this section in particular. So we do this by using, we can do this at the most basic level by simply disabling interrupts. So we can have a function like this that locks the interrupts, and then we can have a corresponding unlock function that restores the original state of the interrupts. And we would be basically disabling interrupts first here, and then after this function succeeds, now we cannot be interrupted by any interrupt handler here, so we can do our operation, and if any interrupt handler occurs during this time, then it will be deferred until the interrupt state has been restored. So we can add 8 to this variable, then the interrupt state is restored, and then the interrupt routine runs, adds 5 to it, and we get the correct result. Now, the Spinlock is a generalization of this approach. So the problem with the approach that I've just shown you here is that this approach will not work if we have multiple cores, because interrupts are always local to one processor core. So essentially, even if we use this code and we simply disable interrupts and then re-enable them again, on a multi-core system, let's say that this interrupt would execute on another core. On a multi-core system, the interrupts are only disabled on the core we are currently running on. So this wouldn't protect us from another core executing this interrupt routine, messing up the data, and then we would still get the wrong result. So we need a better approach that also protects us against other cores that might execute interrupt handlers that would also try to access the same data, or even any other code that just tries to access the same data concurrently. And for this, we use the Spinlock. So the Spinlock is a generalized approach that has 2 operations executed. Number 1 is that it disables interrupts, just like before. And number 2, it has an atomic variable that it tries to set atomically. So it tries to compare that variable and then set it to a value of 1, for example. And if the comparison is successful, then the value is set. If the comparison is not successful, then the operation loops until it is able to set to compare and set the value atomically. And if multiple CPUs try to acquire the Spinlock, basically we cannot set this variable atomically on more than one CPU at the same time. If one succeeds, then the other ones will fail, and so the operation will loop. And we can see this in the code here. So we have our, first of all, we lock the interrupts. And the reason that this function is, for example, implemented as architecture-specific RQLock is because here we want to lock interrupts just by disabling the interrupts. Now, on Zephyr in particular, the normal RQLock without the arch, it's actually implemented as a Spinlock in order to be compatible with multi-core systems, because originally Zephyr did not support multi-core, so RQLock was used. And then to make sure that old code doesn't break on multi-core systems, the public function RQLock has been replaced by a global Spinlock. So it essentially translates to a Spinlock. So if we implement Spinlock, obviously we cannot use the global function that will have another Spinlock. Instead, we use the raw function that simply disables interrupts. So we disable interrupts. We store the original interrupt state here so that we can restore it later. And we then loop on the atomic compare and swap operation. And this basically translates to compiler-specific compare and swap that is guaranteed to be atomic. So it will compare this locked value to 0. If the value is 0, then it will set it to 1. If the value is not 0, then it will return a failure. And so we will loop in this loop until we are able to set it. So essentially, what this means is that if another CPU executes this code, it's going to loop and wait until we release the lock before it can continue. And in the unlocking operation, we clear this atomic, and then we basically we do these operations in reverse order. So we clear the atomic, and then we unlock the interrupts. We restore the interrupt state. And the reason we have to store the interrupt state and then restore it is because it's perfectly valid to try to lock another spin lock that is not the current spin lock, but another spin lock, and then unlock it. And we don't want to simply enable interrupts because that would be wrong. We want to restore the state instead. The best practices of spin locks is that we should only use spin locks when we need to lock data very momentarily. So we shouldn't be holding a spin lock for longer than absolutely necessary. And the second best practice is to we can use the spin locks even on bare metal. We don't need to have an RTOS in order to benefit from this pattern. So we can use it even without an RTOS, even without a scheduler, simply where we need to synchronize between interrupt access and normal code access to a particular data structure. The two main pitfalls of spin locks that you would want to avoid is locking across functions. So if you're holding a spin lock across multiple functions, it usually means that maybe you need to simplify your code a little bit so that you can avoid holding spin lock across function boundaries. Because if you're calling another function, then it's not always clear what that function is going to do, and also what that function is going to do in the future as the application evolves. So you might inadvertently maybe expand that function that's being called, and let's say that function takes longer time now, but you're not aware that this function is called with a spin lock held, and so your application gets too much interrupt latency in particular cases, which are also hard to debug because it would only happen if there is events happening at the same time. So you will get a latency in some cases, and in some cases it would just work fine. So it becomes hard to debug, and to avoid this, you try to just lock for very short periods of time and only in places where you're just accessing the data. And just keep this code very simple and don't call anything outside of the function. Just do the operation very briefly and then release the spin lock so that all the events can be processed as normal. The two main alternatives to Spinlock is just raw interrupt disablement. So you can still use RQ lock, but the problem is that that code would not be scalable. And for example, if you look at the implementation of spin locks and RQ disable, in particular RQ lock, RQ unlock on Zephyr platform, then you will see that on a multiprocessor system, RQ lock actually translates to a global spin lock. And the reason for that is because RQ lock doesn't really help you on a multiprocessor system, so it doesn't really make any sense. And for that reason, the spin lock pattern has been created as a generic way of generalizing the critical sections across both single processor systems and multiprocessor systems. So you should really always try to use the Spinlock pattern instead of raw RQ locking and unlocking. And the second alternative is scheduler locking, when you just lock the scheduler itself. But this approach also only works on threads. So it doesn't help you synchronize your data access between your application code and interrupt service routines. It just works between multiple threads where you prevent scheduling during the time when you're inside this critical section. So Spinlock pattern is really something that almost doesn't have any really viable alternatives. It's kind of the lowest level pattern that interfaces with hardware. And then on top of this pattern, we can build very robust primitives that become more aware in terms of being aware of threads, being aware of the scheduler, And then we can, on top of that, we can build all other more complex paradigms, such as, for example, event queue, work queue, and things like that. So the Spinlock is kind of the lowest level interface to hardware and to the concurrency that is actually present inherently in the hardware itself. All right, so in this lesson we covered Spinlocks. I've shown you an implementation of the Spinlock. I've shown you the two main operations that the Spinlock does, and I've also explained why we need both of these operations in order to create robust critical sections on any type of system, even if we have multiple CPUs present. Now we're ready to move into more complex patterns. We're going to look at the semaphore, we're going to look at the mutex, and we're also going to look at conditional variables that give us a foundation for more complex patterns to be implemented on top of that. But before we do that, let's do a little quiz. And to check your understanding of Spinlocks, let's go through all of these questions. So what main problem is the Spinlock abstraction designed to solve? Why does modern implementation of Spinlock always disable interrupts on current CPU before trying to acquire the lock? What would happen if we didn't disable interrupts and we tried to acquire the lock? What problem would we run into? Why is it important to save original interrupt state into this key variable on the stack when you acquire a Spinlock, and then to restore interrupt state when you release the Spinlock? Why is it important to hold Spinlocks, to not hold Spinlocks across function calls? What code/operations does a Spinlock locking and unlocking essentially translate into on a single core system? Is it fine to attempt to lock another Spinlock while holding a different lock? Why should you always use Spinlock pattern instead of low-level interrupt enable disable, even if you don't have direct plans to support multi-core systems? And why is it completely wrong to compare Spinlocks to mutexes or semaphores or any other thread-aware synchronization primitives? All right, that's it for this module. I hope you can use this information. I hope it gives you a basic understanding of the lowest level primitives. And now let's move to other primitives in the next module.